Hi, so today we'll be seeing an example of how to solve a paging question in operating systems. So let's see the question first. So as you can see here, your logical address is of 28 bits and physical address size is 34 bits. Page size is 2 KB and page table entry size is 4 bytes. Okay. Now your memory is byte addressable. What does it mean? It means that each location will store 1 byte of data. Okay. So now let's first of all uh, visualize the problem. So your logical address, as you can see, is 28 bits. Okay. So you can see like this is your logical address. Okay, and it is of 28 bits. 28 bits. Now from the logical address, as we know that a prefix is the page number. Okay, so it will be divided into two parts. It will be byte of the first one is the page number. Okay, and the second one is byte offset. Byte offset. So as you can see the page size, okay, you have given a page size. So this is, so now let's first understand how to find the process size, okay? Process size. So as you know, the logical address is nothing but related to your process only, and the process size is 2 raised to the power 28, since you have 28 bits, and each location. So this is your process, and there are several locations. Okay, how many locations you have? You have 2 raised to the power 28 locations, and each location is storing 1 byte of data. So your total process size becomes 2 raised to the power 28 bytes. Okay. Now next thing is number of pages. Okay, number of pages. So now you can see that this is your process, and each page size. So what is the page size in the question? 2 KB. Okay. So your page number of pages will become process size divided by page size. Okay. So your process size is 2 raised to power 8 bytes divided by page size is 2 KB. That means 2 multiplied 2 raised to power 10. This is for kilo and bytes. Okay, and this is also bytes. So bytes cancel. This will become 28 minus 11. So it will be 717. Okay, so these how many pages, these pages you have. Now you have how many pages? 2 raised to the power 17 pages. Now to represent 2 raised to the power 17 things. Okay, things means pages. Okay, in binary you would need 17 bits. Okay, or you can say like where is the question to find the number of bits required for page number, yeah, from this fifth question. Okay, so for the fifth question's answer, number of bits required for page number is log base 2 is number of pages. Okay, so it will be number of pages. So log base 2, 2 raised to power 17 pages you have. This will give you 17. Okay. So from 28 bits here in the logical address, your page number bits required for page number will be 17, and the left bits, okay, left this section uh, will have how many? 11 bits. Okay. So now let's go to the third part, which is main memory size. Okay, what is your main memory size? So this will be 2 raised to the power physical address bits. So how many bits you would need? 34 bits, as you can see here. Physical address requires 34 bits. So main memory size will be 34. And since so similarly you can also visualize it. This is your main memory, and there are how many locations? These are your locations. 2 raised to the power 34 locations. Okay, and each location will be having 1 byte of data. So this will become 2 raised to the power 34 bytes. And what is the fourth part? Number of frames. Yeah. So number of frames. So this is main memory size divided by frame size or page size. Okay, both, because frame size and page size have to be equal. So it will become 34 bytes divided by 10 bytes. 34 minus 11, it will become 3 2. Yep. 23. So these many frames you will have in your main memory. Okay, so fifth part we have already done. Number of bits required for page number, log base to number of pages, it will give you 17 bits. And similarly for frame number you can find out. So this is your sixth part. Number of bits for frame number. As you can see, you have how many frames? The log base 2 number of frames is 2 raised to the power 23. This will give you 23 bits. Okay, so you can see to represent a frame. So this is your main memory. Okay, this one. And so let's suppose this is your one frame. So to represent a one frame, you would need how many bits? 23 bits. Okay, so like 0 0 0, like for example the frame 0 will have 0 0 0 for how many times? 23 times. Okay. And then seventh part, number of entries in page table and page table size. So you can see your, so first of all let's see your page table. Okay, so your page table will have how many entries? So number of entries in page table will be equal to number of pages, as we know, because for each page, so one page, for a page for page 0 you will have an entry, then for page 1 you will have an entry, then for page 2 you will have an entry. Okay, this way. So you will have how many pages? Go above. You have 2 is about 17 pages. Okay, and each page table entry size is 4 bytes. Okay, so for to store this, but one so mapping for one page you would need 4 bytes. That means 4 into 8 is 32 bits. But as you can see, your frame number requires only 23 bits. Okay, so out of 32 bits, 23 bits are required to store frame number. So you can see these 32 bits are for frame number. Okay, and the rest of the bits, 32 minus 23, so 9 bits are reserved for, are available for extra information, as I have already told you. Extra information, so what extra information? Maybe valid bit, maybe modified bit, or some other information. Okay, so uh, yeah, so here, from here you can see how many entries you have. So number of page table entries you have, number of page equal to number of pages equal to number of pages, and it will be 2 raised to the power 17. And so each page table entry sizes you have given 4 bytes. So your page table size will become 2 raised to the power 17 multiply 32 bits. Okay, or 4 bytes. So you can simplify it. Okay, 2 raised to the power 17 into 4 bytes. Okay, so 2 raised to the power 2 bytes. And more you can simplify it, 2 raised to the power 7 into 210, 2 raised to the power 2 bytes. Okay, now this 2 you can keep as kilo for kilo, and these 2 7 and 2 is power 2 becomes 2 9 kilobytes. It will become how many? I guess 512 kilobytes. So this is your whole page table size. Okay, whole page table size. So I think, yeah, that's all. That's all the seventh and So number of page table entries is for 7th and this is for 8th. Okay, so this is how you solve a question related to paging, given you have logical address, physical address and other things. Okay, thank you.